Some years feel like a normal page turn in the cosmic calendar, and then a year arrives that feels like the universe leaning closer. 2025 was that kind of year. The sky did not explode with a single loud headline. It whispered dozens of strange answers at once. A visitor from another star system drifted into view, and suddenly our solar system did not feel like a closed neighborhood anymore. A black hole revealed itself without a flash, just by the way nearby stars were forced to move. A nearby planet that somehow avoided the spotlight started looking a lot more interesting. If you want to follow the trail of these discoveries with us, like this video and subscribe. Every so often, science gets a year that feels quietly different. Not because one thing changes, but because the pattern changes. The questions we ask start to evolve. The tools we use start to see past the tricks that nature has been using on us. And the universe, with that strange sense of humor it has, seems to reward the better questions first. This is not a story about a single miracle instrument that solved everything overnight. It is a story about a growing nervous system spread across Earth and space, where telescopes, surveys, and teams of people react faster than ever. It is a story about better software, better coordination, and a deeper willingness to admit when an old assumption was simply comfortable. And the wild part is that the biggest moments of 2025 do not even belong to one category. Some are about our own solar system, which we tend to treat like familiar territory. Some are about distant galaxies, where time itself behaves like an optical illusion. Some are about the possibility of life, which is always the real tension underneath the science, even when nobody says it out loud. So before we dive into the first discovery, let's do something simple together. Imagine you could choose only one confirmation, one phone call from the universe that cannot be mistaken. Would you rather confirm ancient life on Mars, finally proving that biology once happened on another world in our own solar system? Or would you rather find a living world close enough to feel almost reachable, a planet around another star where we could eventually study the air, the weather, maybe even the signs of ecosystems? There is no wrong answer. The fact that we can even ask this question with a straight face tells you something about where astronomy has arrived. We are not just counting rocks anymore. We are trying to understand origins, histories, and possibilities. In 2025, the universe handed us a third confirmed visitor from another star system. That alone would have been enough to define a year, because interstellar objects are not just passing curiosities. They are physical pieces of another planetary system, delivered by chance, carrying chemistry that formed around a different sun. They make the galaxy feel less like empty distance, and more like an ocean with currents. In the same year, we found a black hole in a nearby companion galaxy that was not screaming in X-rays or blasting jets into space. It was quiet. It was hidden in plain sight. It revealed itself the way a concealed predator reveals itself in tall grass, not by sound, but by the sudden behavior of everything around it. When something invisible can push stars into strange motions, you start to feel how incomplete our picture still is. Also in 2025, we took a closer look at a planet orbiting a quiet red dwarf just 18 light-years away. 18 light-years sounds far because the human brain is not built for cosmic distances, but in astronomy terms it is close enough to feel personal. It is close enough to be a target for the next generation of atmospheric measurements. It is close enough to turn the idea of habitability from a poetic word into a testable hypothesis. And then there are the discoveries that remind us how badly we underestimate our own backyard. Uranus, the planet we tend to treat like a pale blue footnote, quietly gained a new moon in our catalogues, spotted by the James Webb Space Telescope, while it was studying the faint structures around the planet. 10 kilometers across is tiny by cosmic standards, but the meaning is not the size of the moon. The meaning is the way we found it. When a telescope can stare long enough and cleanly enough, the solar system starts giving up objects it has been hiding for decades. Mars, meanwhile, continued its slow, stubborn work of tempting us. A rock sample stood out, not because it shouted life, but because it refused to fit neatly into the boxes we prefer. It looked like the kind of puzzle that makes scientists unusually careful with their words, not because they want drama, but because they know how deep the consequences go if the evidence holds up. Far beyond Mars, the early universe also refused to behave. A supermassive black hole was seen actively feeding at a time when the universe was still supposed to be young, still supposed to be building its first big structures. It raised the same uncomfortable question we keep running into with the James Webb Space Telescope. How did the cosmos grow up so fast? How did enormous things appear so early, with so little time to assemble? And if that were not enough, a spiral galaxy appeared in the deep past looking far too settled, far too organized. Spiral structure is not supposed to be easy. It is a fragile kind of order, a balance between gravity, gas, and star formation over long time scales. Seeing that kind of maturity so early is like finding a city with ancient roads and steady traffic patterns in a place where you expected only scattered tents. Then we get the kind of shock that is almost funny, until you realize what it means. Saturn suddenly gained a huge number of moons in our records, enough to rewrite the leaderboard of the solar system. That sounds like trivia until you remember what these moons represent. They are fragments and captures and collisions. They are history in orbit. When the count jumps, it suggests we are finally seeing the full debris field of past events that shaped the planets. Closer still, Earth's neighborhood offered its own reminder that we live in a dynamic system, not a museum exhibit. A near-Earth object was identified as a kind of companion, moving with us in a special orbital relationship that keeps it close over long stretches of time. It is not a threat story by itself. It is a perspective story. It tells you that even near-Earth space is not fully mapped in the way your intuition wants to believe. And finally, as if the universe wanted a philosophical punchline, we got a measurement that challenges one of the most basic numbers about our own motion. In late 2025, surveys of distant radio galaxies suggested that our solar system might be moving through the cosmos, relative to the cosmic microwave background far faster than the standard expectation. That phrase sounds technical, but the idea is simple. The cosmic microwave background is the leftover glow of the Big Bang, filling all of space. It acts like a kind of reference frame, a background against which our motion can be measured. If our speed relative to that background is different than we thought, then the story of our place in the large-scale universe may need a correction. So what is the connecting thread here? Why do these discoveries feel like they belong in the same year? Part of the answer is that science is not only about new objects, it is about new eyes. Sometimes those eyes are literal, like a telescope that gathers more light and sees finer detail. Sometimes those eyes are mathematical, like better data processing that can catch faint patterns buried in noise. And sometimes those eyes are cultural, meaning teams across the world coordinate faster, share alerts faster, and build on each other's work without losing precious time. Another part of the answer is more unsettling. The universe is under no obligation to match the story we expected. It will let us build a neat narrative, and then it will casually hand us an observation that makes that narrative wobble. That wobble is not failure. That wobble is the point. It is the moment where we stop memorizing facts and start learning how reality works. So let's begin where 2025 truly starts to feel unreal, with a comet that does not belong to our solar system at all, a visitor that crossed the dark between stars and arrived without an invitation. And once you really sit with that, the rest of the year starts to look less like a list of discoveries and more like a message. When astronomers first noticed it in July 2025, it looked like the kind of tiny, unremarkable speck that drifts through survey images every night. A faint point of light, moving just enough between exposures to betray that it was not a star. At first, there was no drama, no flaming sky, no world-ending object, just a new track in the data. Then someone ran the orbit. The path refused to bend into a closed loop around the sun. Instead, it traced a hyperbolic sweep, the signature of something that would pass through once and never return. That is when people sat up. This was not local. This was from the deep between the stars. They gave it a name that quietly encodes its place in history, Comet 3I Atlas. The 3 means third known interstellar object. The letter I is for interstellar. Atlas is the survey project that first picked it out of the noise. Hidden in that short label is a big statement. We have now caught 3 solid things that formed around other suns, wandered through the galaxy for ages, and happened to drift through our solar system while our tools were ready. To get a feeling for how strange that is, picture a sleepy port town. Almost every ship that comes in and out belongs to the same coastal network. You know, the paint schemes, the flags, the usual cargo routes. Now imagine one morning you wake up and there is a vessel on the horizon that does not match anything in your shipping logs. Different hull shape, different way of moving through the waves. You have never seen its flag before. That is what an interstellar comet is to planetary science. It is not just another visitor. It is a visitor from a different ocean. Our first such visitor was Oumuamua in 2017, a mystery wrapped in a very small amount of light. It passed so fast and so faint that we never saw more than a moving dot and its changing brightness. It did not grow a classic comet tail. It tumbled. It seemed elongated or perhaps flattened. Its brightness curve suggested unusual shape and surface properties. Then its motion showed a tiny extra push that was not just gravity. For years, scientists argued about what it could be, from exotic ice to shredded fragments. Oumuamua opened the door but left the room dark. The second visitor, discovered in 2019, was Comet Borisov. Where Oumuamua was all ambiguity, Borisov was comfortingly familiar in shape. A clear coma, a proper tail, a body that behaved like a textbook comet, just moving too fast to be bound to the sun. Spectra suggested ordinary ices, though with hints that its chemistry was not an exact copy of what we see in our own comet family. Borisov told us something simple and profound. Other planetary systems likely have icy outer reservoirs that fling comets into space just as ours does. Now we arrive at 3I Atlas, and suddenly the pattern sharpens. This object combines the best of both earlier cases. It is clearly a comet, complete with tail and coma, so we do not have to argue about whether it is icy or dusty. At the same time, its orbit screams interstellar. Its speed and hyperbolic trajectory cannot be produced by any normal perturbation inside our own planetary system. It is not falling in from the distant Oort cloud. It is passing through from somewhere else entirely. Here is the detail that made astronomers lean in. This thing is big by interstellar visitor standards. Estimates put the nucleus at roughly 5.5 kilometers across, on the order of 3.5 miles, about the length of 56 football fields laid end to end. Oumuamua, by comparison, was probably only a few hundred meters from tip to tip. Borisov was also on the small side for a comet. Larger objects are brighter, which gives us more time to spot them and more time to watch them in detail as they come and go. Size matters for another reason. Think about what happens to any object wandering between stars for billions of years. It is bombarded by cosmic rays and tiny dust grains. Its surface gets altered, eroded, rearranged. Smaller bodies can be turned inside out by this slow sandblasting. Larger bodies keep more of their original interior safe. They are like thick old books that still hold the full story because their pages are not all worn away. When you get a big interstellar comet, you are looking at a better preserved sample of the place it came from. That is why 3I Atlas feels less like a curiosity and more like a delivered lab sample. We cannot yet send starships to alien planetary systems. The travel time would be measured in many thousands of years with current technology. Yet here is a chunk of another system, thrown free long ago, crossing our orbit almost as an afterthought. The only price of admission is that we notice it in time and point enough instruments at it before it fades back into the dark. The moment the orbit solution confirmed this visitor was unbound, a familiar pattern kicked in. Survey telescopes raised the flag. Then bigger observatories took over, space-based telescopes that can stare above Earth's atmosphere, and ground-based giants that can spread the light into spectra and tease out composition. The point is not that one magical telescope did everything. The point is that each one sees the comet in a different way, like a team of doctors reading the same scan with different specialties. All of this effort rests on a simple emotional truth that scientists usually hide behind careful language. There is something deeply moving about knowing that the photons hitting your detector left the surface of an object that formed around another star entirely. You could draw a line backward through space and time that ends in a place where different planets spun around a different sun under different skies. And yet, a piece of that story is now bright enough for us to study with tools we built on a small rocky world far away. Of course, the story of 3I Atlas is not just about romance. It is also geometry and detective work. If you know the comet's position on the sky at many points in time, and you know its distance and speed, you can rewind the trajectory. You can trace its path backward to see roughly which direction in the galaxy it came from. In the case of this comet, that reconstruction suggests an origin among the nearby stars within a few tens of light years. Not next door in human terms, but close enough that we can point out the region on a map of our local neighborhood. There is a classic comparison astronomers like to use here. Imagine a bullet found embedded in a wall. From the angle and the shape of the grooves, you might be able to work out which kind of gun fired it, and roughly where the gun was when it fired. In this analogy, the bullet is 3i Atlas. The wall is our solar system. The flight time is measured not in seconds but in cosmic ages. Yet the principle is the same. The trajectory carries a clue to the event that launched it. And remember, this is the third time in less than a decade that we have seen such a thing. Before Oumuamua, many models assumed interstellar objects would be rare, maybe once in the lifetime of our instruments. Now we have enough detections to start suspecting the opposite. These travellers might be fairly common. We simply did not have wide enough, sensitive enough surveys before. Our skies were full of messengers, and we were just not listening carefully. If that is true, then 3i Atlas is not a freak event. It is part of a slow, quiet exchange of material between planetary systems. Every time a giant planet in a distant system nudges a comet hard enough, it can eject it forever. Those cast-offs drift through the galaxy, crossing paths with other stars including ours, and our own system is likely doing the same thing, flinging its own fragments into the void. Once you see it that way, the Milky Way stops feeling like a set of isolated islands and starts feeling like an ocean with drifting debris and shared ingredients. By itself, the discovery of a large interstellar comet already tells us that the architecture of other systems is not wildly different from our own. They have rocky inner regions and icy outer reservoirs. They have giant planets that can act as gravitational bouncers, kicking things out permanently. But the real treasure is not only where the comet came from, it is what the comet is made of. Light reflected from its surface and emitted by its gases carries a chemical fingerprint. That is where the story of 3i Atlas turns from an orbital curiosity into a deep origin question. Because with a visitor this large and bright, our instruments can do more than just track its motion. They can read that fingerprint in detail, and from it, they can start to reconstruct the environment in which this object froze into existence. In other words, we can begin to listen for its accent. When people talk about an accent, they mean more than sound. An accent tells you where someone grew up, what language they heard as a child, sometimes even what kind of neighborhood shaped them. Astronomers borrow the same idea when they talk about the chemistry of a comet. The mix of gases that boil off, the way dust grains reflect light, the ratio of one molecule to another, all of that becomes a kind of spoken history. If 3i Atlas is a visitor from another star, its accent is our best chance to hear where it came from. The first step in listening is not romantic at all. It is spectra, lines of colour spread out from the light of the comet like a code. When sunlight hits its surface and when solar heat turns its ices into gas, atoms and molecules absorb and emit very specific colours. Run that light through a spectrograph and you get a barcode pattern. Different bars, different molecules. Water, carbon monoxide, carbon dioxide, cyanide radicals. Simple organics, each one leaves its own mark. Comets in our own solar system tend to fall into rough families based on those patterns. Some are rich in carbon monoxide, some are relatively dry, some carry surprising amounts of complex organics. These differences are not random. They reflect the temperature zone where the comet formed, how far from the young sun it froze, and how much processing it has endured since. A comet that formed in the cold outer regions preserves fragile ices that would never survive closer in. When telescopes turned toward 3i Atlas, one feature jumped out early. The signature of carbon dioxide was unusually strong. That does not mean it was the only gas present. There was water vapour from thawing ice. There was likely carbon monoxide as well. But the relative strength of the carbon dioxide features suggested a formation environment that was colder or chemically different from the places where most of our long-period comets formed. Imagine walking into a crowded room and hearing someone speak with a familiar rhythm, but with vowel sounds that are just slightly off from any region you know. You cannot place it immediately, but you know it is not local. That is what an enriched carbon dioxide signal feels like to comet scientists. It hints at a protoplanetary disk around another star that cooled in a different way, or that drew its raw material from a different blend of interstellar clouds. Of course, a single gas ratio cannot tell the whole story, so astronomers layered their measurements. Space-based telescopes like Hubble watched in ultraviolet and visible light, tracking how the coma brightened as the comet approached the sun. Infrared instruments measured heat, and caught faint signatures of dust minerals and organic molecules. Ground-based observatories with wide mirrors and stable spectrographs stared for as long as they could, trying to pull out the faintest features from the noisy background. Over weeks and months, a portrait started to form. The dust released by 3I Atlas looked broadly similar to dust from our own comets, but not identical. Grain sizes, reflectivity and colour slopes all hinted that the building blocks of this body were drawn from the same galaxy-wide pantry, but baked in a slightly different oven. The gas mix reinforced that idea. This was not an alien chemistry that broke all the rules, it was a familiar recipe with different proportions. That may sound almost disappointing at first. You might expect a visitor from another star to be wildly exotic. In reality, the fact that it is not is the most important part. It suggests that planetary systems across the Milky Way are making comets out of similar ingredients, under similar physical laws, with only local variations. That means our solar system is not a strange exception. It is one example of a broader pattern. There was another clue hidden in the way 3I Atlas responded to sunlight. As it approached the sun, its level of activity climbed in a very specific curve. The timing of when different gases turned on and off, the way jets of gas and dust changed direction as the nucleus rotated, all of that could be modelled. Those models suggested that its outer layers had been processed, cooked slightly by long exposure to background radiation, while its interior remained relatively pristine. Translate that into a story and you get something like this. Long ago, roughly when our own solar system was forming, another young star built a disk of gas and dust. In the cold outer regions of that disk, small icy lumps grew into larger ones. One of those became the nucleus that we now call 3I Atlas. Over millions of years, gravitational nudges from larger bodies pushed it into an orbit that crossed paths with a giant planet. That encounter slingshotted it out of the system entirely. From then on, it wandered interstellar space, slowly aging on the surface while its core stayed frozen in time. That timescale matters. If its formation age really lines up with ours, that means the galaxy was seeding planetary systems with similar materials at the same cosmic moment. It also means that for billions of years, bits of those systems have been quietly trading places, passing each other in the dark. We just did not know how to listen until recently. All of this analysis grew more urgent as late 2025 approached. That was when 3I Atlas reached perihelion, the moment of closest approach to the Sun. Comets are at their most talkative near this point. Heat forces more gases to sublimate, more dust to lift off, more jets to flare. The coma grows, the tail lengthens, the bars in the spectral code become easier to read. At the same time, brightening makes the nucleus harder to see directly. The art is in timing. Observe early and you see the bare rock and ice. Observe late and you see the full fireworks display. During the weeks around perihelion, observatories coordinated like an orchestra. Some focused on high-resolution imaging, trying to catch hints of the nucleus shape between jets of gas. Others leaned into spectroscopy, reading the chemical accent in the most detail possible. Radio arrays tuned to frequencies where certain molecules emit faint signals, hoping to catch complex organics riding in the vapor. Each wavelength told a slightly different version of the same story. And because this was our third interstellar visitor, scientists could start playing a new game, comparison. They placed the chemical fingerprint of 3I Atlas next to what we inferred for Borisov and what little we could deduce about Oumuamua. Even with sparse data, patterns began to emerge. Interstellar objects seemed to span a range of compositions, but none looked wildly impossible. It was as if different kitchens across the galaxy were all drawing from the same recipe book, improvising more in some ingredients than others. There is a deeper reason this matters. Comets are more than pretty streaks. In many origin stories for life, they are couriers. They deliver water, organics, and other raw materials to young rocky planets. If that is true, then the chemistry of comets from other stars hints at the chemistry of possible life on planets we may never see directly. A high carbon dioxide content might change the balance of atmospheres that later form. A richer mix of certain organics could nudge prebiotic chemistry in different directions. None of this is proof that life arose around the star that gave us 3I Atlas. That would be a leap far beyond the evidence. But it does change the flavour of the question. Instead of asking whether life is possible only under an extremely narrow set of conditions, we begin to see that the starter materials for interesting chemistry might be widespread. The galaxy might not be teeming with life, but it is likely teeming with the ingredients. There is also humility in the data. Spectra are noisy. Models have assumptions baked in. Multiple combinations of temperature, composition, and structure can sometimes produce similar signals. So while the story we tell about 3i Atlas is grounded in real measurements, scientists keep alternative explanations on the table. Maybe the high carbon dioxide signal partly reflects surface processing rather than birth conditions. Maybe the dust properties are influenced by collisions long after formation. That is why interstellar objects are not a one-time fascination. The true power will come from a catalogue. 10 visitors, then 50, then hundreds, each with a slightly different accent, each one nudging our picture of how planetary systems build and break apart. The dream scenario is simple to state and hard to execute. Catch one early enough and close enough that we can get a spacecraft there. For now, 3i Atlas remains a drive-by encounter, a conversation shouted between ships passing in the night. But it is the most detailed conversation we have had so far with material from another sun. In the rise and fall of its gas emissions, in the colour of its dust, in the strength of its carbon dioxide voice, we are learning to hear how another corner of the galaxy once froze into solid form. And as its brightness peaks and then begins to fade, as its tail thins and the coma shrinks, one feeling hangs over the data. This will not be the last time. The sky is full of these accents, drifting through at all hours. Now that we have finally learned to listen, the universe is unlikely to fall silent again. By the time 3i Atlas was fully in the spotlight, a quiet realization was spreading among astronomers. Maybe this object was not the rare cosmic lottery ticket we once imagined. Maybe the rare thing was us finally noticing. For decades, the standard story said that an interstellar object might pass through the inner solar system once in a very long while. Oumuamua in 2017 and Borisov in 2019 already cracked that story. A third visitor in less than 10 years does more than crack it. It suggests we were wrong about how busy interstellar space really is. To understand why, you have to zoom out from the comet itself and look at how planetary systems live their lives. When a young star forms, it is wrapped in a disk of gas and dust. Inside that disk, small grains collide, stick, grow into pebbles, then into boulders, and eventually into planet-sized bodies. The process is messy. There is no polite rule that says every rock finds a home. Giant planets form too, and their gravity is brutal. Anything that comes too close can be flung inward toward the star or outward into the cold, never to return. Our own solar system is proof of this chaos. Take Jupiter. Its enormous gravity has been shaping the orbits of comets and asteroids for billions of years. Sometimes it acts like a shield, kicking dangerous objects away from the inner planets. Sometimes it acts like a slingshot, throwing comets into the deep outer cloud where they sleep for ages on stretched orbits. And in many simulations, Jupiter and its siblings do something else entirely. They give small bodies such a strong gravitational kick that those objects reach escape velocity and are ejected from the solar system altogether. Once that happens, the object is no longer a citizen of our system. It becomes a drifter in the Milky Way. From that moment on, it orbits the galactic center directly, not our sun. It spends millions or billions of years in the dark between stars. Sometimes it passes near other systems. Usually it just keeps going, almost never noticed. But once in a while, the geometry lines up. A wandering rock or comet intersects the region around another star at just the right angle to pass through that system before moving on. If our system routinely throws debris out this way, then every other system with giant planets is probably doing the same. That means the galaxy is not a set of sealed solar bubbles. It is an ongoing exchange of material. Icy bodies from distant disks are constantly being launched into interstellar space, drifting and occasionally cutting through the outer edges of someone else's planetary family. When you frame it that way, 3i Atlas stops looking like an exception and starts looking like a sample from a vast invisible population. This is where estimates get wild in the best possible way. Once you have a few detections and you know how wide and deep your surveys are, you can run the clock backward. How many interstellar objects would have to exist for us to have seen 3 in such a short span? The answer is not a handful. It is likely many, many more than we can directly detect. Most would be small, dark, and pass far from the sun, never growing bright enough to register as anything more than background noise. That is the humbling part. The space between stars, which we used to picture as almost empty, might be threaded with uncountable little worlds, fragments, and ice balls. They are not organized into neat orbits. They follow long, lonely paths set by old gravitational kicks and the slow pull of the entire galaxy. 3i Atlas is just one that happened to wander through our searchlight beam while our instruments were finally good enough to notice. There is another twist. This exchange is not one way. Our own system is almost certainly contributing to the clutter. In the early days of planet formation, Jupiter and Saturn would have flung an enormous number of small bodies outward. Some ended up in the distant Oort cloud, barely bound. Many more would have been ejected completely. Even now, rare close encounters can still throw an asteroid or comet over the edge. Those objects become interstellar travelers just like 3i Atlas, carrying the chemical handwriting of our protoplanetary disk out into the wider galaxy. So when we study an interstellar comet, we are not just spying on someone else's family, we are participating in a kind of galactic recycling program. Material that once orbited a different sun passes through our region. Material that once orbited our sun will sometimes pass near other stars. Over long enough timescales, the borders between systems blur. The Milky Way functions less like a set of isolated laboratories, and more like a slow, chaotic trade route for rocks and ice. This has real scientific consequences. If these travelers are common, they are not just curiosities, they are opportunities. Current technology makes it almost impossible to send a probe all the way to another star. Even our fastest spacecraft would take tens of thousands of years to get there. But interstellar objects reverse the problem. They come to us. They cross our orbit at high speed, but for a short window they are close enough to be within reach of a fast spacecraft. That is where the talk of intercept missions comes in. When 3i Atlas appeared, it arrived too late for any existing probe to adjust course and meet it. By the time any new mission could be approved, designed, built, and launched, the comet would already be dimming and heading back into deep space. So mission designers are exploring a different strategy. Instead of reacting, build a ready-to-go spacecraft ahead of time. Park it at a location where it can wait, fueled and awake, for the alert that a new interstellar object is on the way. The idea sounds simple in words and brutal in engineering. You need a spacecraft with powerful propulsion, able to accelerate quickly once a target is announced. You need instruments that can handle high-speed flybys, gathering meaningful data during a brief encounter. You might even dream of sample collection, grabbing grains from the comet's coma as you pass through its environment. And you have to design all of this before you know what the target will look like, how bright it will be, or exactly what path it will take. Yet the payoff is almost impossible to overstate. Landing on or even closely flying by an interstellar comet would turn our telescope's distant spectra into up-close measurements. We could map the surface, drill into the outer layers, analyze freshly exposed material, and directly test ideas about how it formed. Instead of reading an accent from across a crowded room, we would be sitting at the same table, listening in detail. Even without such a mission ready, the appearance of 3i Atlas already changed how the community operates. Observers scrambled to coordinate. Observation time on major telescopes was rearranged at short notice. Data was shared rapidly between teams in different countries. Work that once would have taken weeks of email and planning unfolded in days. In that sense, this comet was a rehearsal for the future. It revealed not just the galactic exchange of rocks, but the global exchange of information. It also forced a psychological shift. We are used to thinking of our solar system as bounded. Charts draw a neat boundary around the planets and the distant cloud of comets, then label everything beyond as interstellar space. The truth is messier. Our region of space is porous. Visitors cross the line in both directions. The sky above you at night is not just lit by distant stars. Somewhere out there, moving silently against that background, are stray pieces of other suns, and perhaps stray pieces of ours still drifting. So when you hear the phrase galactic exchange program, it is not metaphor. It is a literal flow of solid objects swapping places over ages. Some carry water, some carry complex organics, some are ancient rubble stripped of almost everything. Together they tell us that planetary systems do not stay sealed. They share. They contaminate each other. They spread their ingredients across the disk of the galaxy. And once you see the Milky Way that way, everything else in this story feels different. The discovery of a new moon around Uranus is no longer just a local curiosity. It is another clue about how systems build structure and then rearrange it. The strange rock on Mars becomes a potential sample, not only of that planet's past, but of what might be possible anywhere the right conditions arise. Each new find slots into a larger pattern. The universe is not a static museum. It is an active network of moving parts, exchanging material and information across impossible distances. By the time we had wrapped our heads around visitors from other stars, the universe quietly reminded us that we still had not finished counting rocks in our own backyard. In early 2025, astronomers pointed the James Webb Space Telescope at Uranus for what sounded like a routine job. Study the faint rings, map their structure, measure their glow. Nothing flashy, just careful housekeeping on a distant, cold world. Then, tucked against the glare of the planet, a tiny point of light refused to behave like anything on the background starfield. Frame after frame it moved with Uranus, but not exactly with the rings. The system had been hiding one more moon. On paper, that small world is almost an afterthought. It has the provisional label S20 It is roughly 10 kilometers across, about the size of a city. In the language of planetary science, that is barely a pebble. But the pebble carries an important message about how we look at the outer solar system and why routine observations with a telescope like Webb are anything but routine. To feel why this is such a big deal, it helps to remember how ignored Uranus has been. It is the butt of jokes, the sideways spinning ice giant that never gets the good camera time. We have sent orbiters to Jupiter and Saturn, landers to Mars, a probe into the atmosphere of Titan, and even a visitor to Pluto. Uranus, by contrast, has had exactly one brief encounter. Voyager 2 raced past it in 1986, snapped a set of images on the way, and kept going into the dark. Those Voyager pictures changed our understanding of the planet, but they came with brutal limits. The spacecraft was moving fast. It had to keep exposures short to avoid blur. Its detectors were far less sensitive than modern instruments. The rings of Uranus are dim, narrow, and made of dark material that reflects very little sunlight. Any tiny moon nestled near them would be competing with glare, noise, and motion all at once. A 10-kilometer rock with a dark surface could easily hide in that chaos. The James Webb Space Telescope lives a very different life. It sits at a stable point beyond Earth called L2, about 1.5 million kilometers out, where the Sun, Earth, and telescope line up in a way that keeps temperatures steady. Webb can stare for hours at the same patch of sky without the frantic flyby constraints that Voyager faced. Its mirror is more than 6 meters across, so it gathers far more light. Its infrared eyes are tuned to wavelengths where cold objects and dusty rings glow gently against a darker background. In February 2025, a team used Webb to observe the Uranian ring system in exquisite detail. They wanted to understand how the rings are arranged, how bright they are, whether there are any hidden structures. As they processed the data, they noticed a point of light near the rings that did something important. It showed up in multiple exposures. It shifted position in a way that matched Uranus's motion, but did not match any known satellite. It was too persistent and too well behaved to be an artifact. Follow-up analysis clinched it. The tiny dot traced a consistent orbit around Uranus. It was not a distant background object sliding by coincidence behind the planet. It was bound to the ice giant. A new moon had been sitting there, crossing and recrossing the sky for as long as humans have been watching Uranus, and we simply had not seen it until the right telescope looked long enough. With that, the family count changed. Uranus now has 29 known moons. That is still fewer than Jupiter with its 95 or Saturn with its 146, but it continues a trend. Each time we build a more sensitive instrument, the census of small worlds grows. We are not adding giant world-shaping bodies. We are filling in the faint end of the population, the rubble and captures and shattered fragments that record the messy history of these systems. S2025U1 is almost certainly what astronomers call an irregular moon. Regular moons tend to have nearly circular orbits in the same plane as the planet's equator, moving in the same direction as the planetary spin. They likely formed from the same disk of material that built the planet itself. Irregular moons do not follow those rules. They often loop on stretched, tilted paths, sometimes even orbiting backward relative to the planet's rotation. The leading idea is that they are captured objects, stray asteroids, or Kuiper belt bodies that wandered too close and were trapped. A 10-kilometre world on an odd orbit would fit that captured story well. Perhaps it was once a free-ranging icy object in the outer solar system. Perhaps a long ago three-body encounter bled off enough energy for Uranus to claim it permanently. Maybe it was even part of a larger body that was torn apart by tidal forces or a collision, leaving fragments behind on related paths. By plotting the orbit of this new moon and comparing it with the other irregular moons, scientists can start to test these scenarios. There is also a link to the rings themselves. In many planetary systems, small moons act as shepherds, using their gravity to herd ring particles into narrow, sharp-edged bands. Saturn provides the classic examples. Uranus likely has shepherd moons as well, but because its rings are so faint, the search has been harder. A new little satellite near the rings immediately raises the question of whether it is shaping them in subtle ways. Its gravity, though weak, could still sculpt the distribution of dust and ice over long timescales. All of this would already make the discovery scientifically interesting, but there is a larger context. Uranus and its cousin Neptune represent a whole class of worlds we barely understand. More than half of the exoplanets we have found orbiting other stars are similar in size and mass to these ice giants. That means if you pointed at a random planet-sized object in our galaxy, there is a good chance it would look something like Uranus. Yet in our own system, we have only one hurried flyby's worth of close-up data to work with. That gap is why planetary scientists have been pushing hard for a dedicated Uranus mission. An orbiter that could spend years mapping its atmosphere, its magnetic field, its rings and its moons would be a treasure trove, not only for understanding this one planet, but for interpreting countless exoplanets. The discovery of S2025 View 1 feeds directly into that planning. Any future spacecraft will need to navigate through a complex system of small bodies. Knowing where those bodies are is essential for both safety and science. Imagine designing a tour of the Uranian system without realizing there is a 10-kilometre moon crossing one of your planned trajectories. At the distances and speeds involved, even a small rock could be dangerous. On the flip side, if you know that moon is there, you can target flybys to sample its composition, map its surface, and watch how it interacts with nearby rings. A single faint dot in Webb's images translates into real constraints and real opportunities for a mission that might not launch for more than a decade. The composition of the new moon is still uncertain. Webb cannot easily resolve an object that small and far away. Based on similar irregular moons, scientists suspect it is a mix of rock and ice with a dark organic coating on the surface. Radiation in the outer solar system tends to break apart simple molecules and reassemble them into complex tar-like material that darkens over time. These coatings make small moons even harder to see in visible light, which is one more reason it took an infrared powerhouse like Webb to find this one. In that sense, S2025U1 is a perfect symbol of where we are in exploration. The big, obvious worlds are all discovered. The headlines are no longer about uncovering an entirely new planet in our system. They're about finding the small, subtle pieces that complete the puzzle. They're about using instruments designed to study the first galaxies in the universe to notice a tiny local moon that everyone else missed. It also answers the question of what routine observation means with a telescope like Webb. There is no such thing as routine. Point it at a ring system and you might catch a new satellite. Aim it at a star-forming region and you might see planets still wrapped in disks of gas. Turn it toward a distant galaxy and you might find a black hole that grew too quickly for our theories. The lesson is the same in every case. When your eyes improve, the universe quietly reveals that it had more to show you all along. By the time the news came out in September 2025, Mars had already spent decades teasing us. We had seen dried riverbeds, mineral veins that only form in water, even meteorites that carried strange chemistry. Each time, the story got close to the word life, then backed away. So when NASA held a briefing about a single rock in Jezero crater, the wording was careful. No one said we had found life on Mars. What they said was more unsettling. This rock was behaving as if life might have been involved, and the non-biological explanations were running out of room. To see why this matters, you have to rewind to why Perseverance went to Jezero in the first place. Jezero is an old impact crater near the Martian equator that once held a lake billions of years ago when Mars had thicker air and flowing water. A river cut through the rim and built a delta, spreading layers of mud and sand into the basin. On Earth, deltas and lake sediments are some of the best places to look for preserved signs of ancient life, because fine particles settle gently and can bury delicate structures. If Mars ever hosted microbes on its surface, a place like Jezero is where their traces would have the best chance to survive. Perseverance is basically a rolling geology lab. It can drive across the ancient lake bed, drill into rocks, and look at them with cameras that see more than human eyes ever could. Early in the mission, the rover sampled a piece of fine-grained rock in the delta region and tagged it with a name, Chayava Falls. On the outside, it looked like what you would expect from an old lake deposit, layered and compacted over immense time. Mud that had once settled quietly through water had been pressed into stone. Then the anomalies started to show up. Under close-up imaging, Chayava Falls was not uniform. Scattered across its surface were tiny spots that looked different from the surrounding rock. These patches were enriched in organic compounds, meaning carbon-bearing molecules, and each one was wrapped in a thin rind of minerals that usually form when water interacts with rock. The combination was like a sentence written in a language we only half understand. Organics, water-related minerals, and a very specific spatial pattern. Organic compounds by themselves are not a smoking gun. Carbon chemistry is common throughout the universe. Meteorites that fall on Earth carry organics. Comets are full of them. You can even make complex organics in the lab by zapping simple gases with energy. So the first job was to ask boring questions. Could the organics in Chayava Falls have been delivered by a meteorite that splashed onto the rock long after it formed? Could purely chemical reactions inside the rock have arranged them into these patches without any biology involved? Researchers attack those ideas with the tools Perseverance carries. Lasers and X-ray spectrometers probed the chemistry of the spots and the rind around them. The organics did not match the typical signature of contamination from known Martian meteorites, and they were too neatly tied to specific layers and textures inside the rock. The water-formed minerals in the rind looked like they had grown in place, as fluids moved through tiny pores while the sediment was still young. It was not the simple picture of a splat from above. What made scientists uneasy was not a single feature, but the way several features lined up at once. On Earth, certain mineral coatings, certain chemical signatures, and certain textures in sediments often appear together in places where microbes once grew in mats or films. Over time, the living cells vanish, but the way they trapped and bound sediments and altered the chemistry can remain. Chayava Falls showed a similar clustering of clues, hints that something once interacted with the rock in a persistent, organized way rather than a random splash. At the same time, everyone involved knew the history. Mars has fooled us before. In the 1990s, a meteorite from Mars called Allen Hills was announced as possible evidence for Martian microfossils based on microscopic shapes and chemistry. Years of follow-up work showed that non-biological processes could probably explain those features. The lesson was painful. The bar for claiming life on another world has to be far higher than the bar for raising the possibility. So this time, the team did what you do when you're trying not to fool yourself. They treated biology as the last explanation, not the first. They built models of how minerals might grow in a cooling rock. They checked whether groundwater could concentrate organics in patches without any microbes helping. They compared Chayava Falls with other rocks in Jezero that had similar histories but did not show the same pattern. One by one, the simple, non-biological stories failed to fit all the data at once. A scientist used a grounded analogy that spread quickly. Imagine you're walking through a forest after a rainstorm, and you see shapes in the mud that could be footprints. At first, you assume they are just random patterns from dripping water and falling leaves. Then you notice they are evenly spaced. They follow a line. Some are deeper in the same way, as if a heavier leg pressed down. You still cannot see the animal, but with each detail, the chance that you're looking at real footprints rather than noise creeps upward. That is roughly where Chayava Falls leaves us. We are staring at a pattern in Martian rock that looks a lot like the after effects of life, but we have not seen the organism itself. We are trying to decide whether we are reading footprints or just clever erosion. The September 2025 announcement did not push past that line. Instead, it formally described the features as possible signs of past life and laid out the alternative explanations that researchers had considered and could not fully support. At this point, the limits of a rover become brutally clear. Perseverance can aim a laser at a patch of rock and read off its elemental mix. It can use a microcamera to capture textures at the scale of grains of sand. It can shine ultraviolet light to make certain molecules glow. What it cannot do is what a full laboratory on Earth can do. It cannot separate and identify individual organic molecules in detail. It cannot measure subtle isotopic ratios that often distinguish biological from non-biological processes. It cannot run dozens of different tests on the same tiny sample until every doubt has been chased down. That gap is not a design flaw. It is a reality of mass, power, and time. You cannot send an entire Earth lab to Mars on a single rover. That is why Perseverance carries a different kind of instrument as well, a drill that gathers cores of rock and seals them inside metal tubes. Those tubes are the real bet. They are meant to be picked up by a future mission and flown back to Earth, where every tool we have can be turned loose on them for years. Chava Falls is one of the samples already collected and cached this way. Somewhere on Mars, a small metal tube now holds a piece of that stubborn rock waiting. If the Mars sample return mission stays on track, that tube could arrive on Earth in the early 2030s. At that point, the careful language can finally be tested. Teams around the world will be able to slice, scan, dissolve, and analyze the sample from every angle the way they would treat a precious meteorite, only this time with full context about where it came from and what it looked like in place. The announcement in 2025 did something important for that mission. It turned an abstract scientific goal into a specific question. Before Chava Falls, sample return could be sold as a general desire to know Mars better. After Chava Falls, it became a way to answer a focused mystery about a particular rock that refuses to behave like a simple piece of sediment. Is this the first hard evidence that life once started on Mars and then vanished? Or is it a reminder that geology can still mimic biology in ways we have not fully mapped? Either way, the implications are enormous. If the sample one day passes every test for an abiotic origin, we will have learned in detail how a lifeless world can produce patterns that look alive. That knowledge will keep us from overreading signals on Mars, on icy moons, or on exoplanets. If the opposite happens and the data eventually lines up with a biological explanation, even cautiously, then we will be forced to accept that life has arisen at least twice in one modest solar system. In that case, the galaxy starts to look less like a rare fluke and more like a garden where life sprouts wherever conditions allow. For now, though, Chava Falls sits in an in-between state. Too strange to dismiss, too ambiguous to celebrate. It is the rock that will not behave, a patient reminder that there is a difference between seeing hints and having proof. To cross that gap, we will need more than careful rover work and press briefings. We will need to solve the hardest problem in this entire story, the problem of proof itself, and decide what level of evidence would finally convince us that we are not the only biology this solar system has ever produced. The strange thing about Chava Falls is that it did more than stir up curiosity about a single rock. It pushed an old, uncomfortable question back into the spotlight. What would it actually take to convince us that life once existed on Mars? Not excite us, not trend for a week, truly convince us in a way that would stand for centuries. The answer to that question is not just about Mars. It is about how we decide what is real in science when the stakes are as high as they can get. On Earth, when a claim challenges our picture of reality, the burden of proof climbs. A new species of frog discovered in a rainforest is exciting, but it does not rewrite the universe. A claim of life beyond Earth does. That means the standard of evidence has to be extreme. Multiple lines of data, independent teams, methods so different that their errors cannot overlap. The deeper the claim, the more ways you need to try to break it before you accept it. That is the proof problem Mars keeps throwing at us. We're not just asking whether a certain mineral formed in water. We're asking whether complex chemistry once crossed a threshold from non-living to living in another world. Rovers like Perseverance are masterpieces of engineering, but they are also compromises. They carry a small set of instruments carefully chosen to survive launch, landing, dust, and cold. They are amazing at showing us where the right questions are, but they are not enough to close the case. Perseverance can tell us that Chava Falls holds organics arranged in suspicious patterns, It can show us textures that echo microbial mats on Earth. It can measure elemental ratios that hint at biology. What it cannot do is run the full battery of tests that a controversial sample would face in a terrestrial laboratory. It cannot take the same grain of rock and push it through 10 different instruments, each with better precision than you can ever fit on a rover. That is where Mars Sample Return enters the story, not as a side mission, but as the main way to solve the proof problem. The plan is conceptually simple. Perseverance gathers cores from carefully chosen rocks, seals them in tubes, and leaves them cached on the surface. A future mission lands nearby, collects those tubes, launches them into Martian orbit, and hands them off to a return capsule that brings them to Earth. After that, they are stored like lunar samples, but with an even more intense focus on contamination control. The details are anything but simple. You have to keep Earth microbes away from the samples, so you do not confuse your own biology with Martian signals. You have to be absolutely certain that nothing dangerous is brought back, even though current evidence suggests Mars is a harsh, deeply unfriendly place for active life. You have to orchestrate launches, landings, and orbital handshakes across 2 worlds whose positions change constantly. It is one of the most complex robotic space projects humanity has ever attempted. Yet the reward is hard to overstate. Once a tube of Martian rock sits inside an Earth clean room, everything changes. Instruments that are far too heavy and delicate to fly can spend months on a single sample. Mass spectrometers can tease apart isotopic ratios in carbon, sulfur, and nitrogen. Microscopes can scan at resolutions that make rover cameras look coarse. Organic chemists can search for patterns in molecules that are very hard to create without biology, like long chains with repeating structures or specific left-handed biases in shapes. Most importantly, all of those measurements can be cross-checked. One group in one country can publish a result. Another group can take a different fragment of the same core and try to either confirm it or tear it down. In science, that process is not conflict. It is quality control. When independent teams agree after years of trying to disprove each other, you get the kind of confidence that a quick rover measurement on a distant planet can never give. Cheever Falls gives that entire effort a face. Before this rock, Mars Sample Return could be described in general terms. Bring back ancient lake sediments, understand the planet's climate history, learn how basalt and water interacted. Those goals are important, but they are also abstract. Once a specific sample starts whispering maybe into the conversation, everything sharpens. We're no longer saying we might one day find an interesting rock. We're saying we have one already, and it is waiting. This is also where the wider implications start to come into focus. Imagine that 2 decades from now, after long and careful work, the consensus lands on a non-biological explanation for the features in Cheever Falls. At first, that might feel like a letdown. No Martian microbes after all, but look closer and the story is still huge. It would mean we had finally mapped out another way geology can mimic biology, something we absolutely need to understand before we start making life claims about icy moons or exoplanets. On the other hand, imagine the opposite. Imagine that layer after layer of analysis points to biology as the simplest explanation. Tiny structures in the rock match microbial textures. Organic molecules show patterns that look like metabolism. Isotopic ratios cluster in ways that, on Earth, are produced by life and nothing else. The data will never reach absolute mathematical certainty. Science does not work that way. But it could reach a level where the alternative, that chemistry alone coincidentally mimicked every biological fingerprint at once, becomes far less plausible. If that happens, we will have to say a sentence that rewrites our place in the cosmos. Life began on Earth, and it also began on Mars. 2 worlds, 1 modest star, 2 separate origins stretched across deep time. They might have traded material through meteorites. They might have influenced each other in ways we do not yet understand. Or they might represent completely independent experiments in turning physics and chemistry into something that can evolve. Either way, the statistics change. If life can emerge twice in one solar system, then the galaxy stops looking like a stark desert. It starts to look like a place where, given enough time and enough worlds, chemistry will stumble into biology again and again. Not everywhere, not inevitably. But often enough that asking whether we are alone shifts from a philosophical question to a practical one. Where do we look next? What signs are most promising? How do we interpret atmospheres and surfaces of distant planets through this new lens? There is another subtle consequence of chasing such high standards of proof. It forces us to be honest about uncertainty. We have to resist the urge to declare victory just because a story is emotionally powerful. The idea of ancient Martian microbes is seductive. It ties into science fiction, into our cultural imagination, into our sense of cosmic loneliness. That is exactly why scientists in the Cheever Falls team kept repeating careful phrases. Possible biosignatures, consistent with, but not diagnostic of, life. Hypotheses to be tested by returned samples. To an impatient ear, that language can sound like hesitation or fear. In reality, it is discipline. If you want people to trust you when you say we may have found life, you need a long track record of saying we do not know yet when you genuinely do not know. The proof problem is not just about having the right instruments, it is about having the right culture. In that sense, the race to bring Mars samples home is not a rush in the usual sense. No one benefits from cutting corners. It is a race against time in a different way. The engineers and scientists planning these missions know that big projects require political will and public support that can fade. They know that windows for launching rockets to Mars open and close in predictable cycles. They know that the next decade is a narrow bridge between what our rovers can already see and what our laboratories could eventually prove. Cheever Falls stands right on that bridge. On one side, it's a pattern in remote data, a rock that refuses simple explanations. On the other side, it is a potential core sample waiting in a sealed tube for a ride home. The proof problem lives between those two sides. To cross it, we have to accept that there are some questions we cannot answer from here, no matter how good our telescopes and robots become. And once you really absorb that, you start to see a common thread with every other discovery of this strange year. A large interstellar comet that begs for an intercept mission, a faint moon of Uranus that demands an orbiter, a suspicious black hole that hints at invisible populations elsewhere, a nearby exoplanet that will only reveal its secrets when we can read its air. The universe is not just handing us data, it is handing us missions. The news broke in a way that felt strangely calm for something so extreme. In March 2025, a team announced evidence for a massive black hole that had never lit up, never flared, never done any of the dramatic things that usually give black holes away. No bright disk of gas spiraling in, no jets screaming in X-rays, just a quiet patch of space in a nearby galaxy, surrounded by stars moving in ways they simply should not. The universe had hidden a monster in plain sight, and the only reason we found it was because a few stars were trying to escape. The black hole lives in the Large Magellanic Cloud, often shortened to LMC, a small companion galaxy that orbits our Milky Way. From the southern hemisphere, you can see the LMC with the naked eye as a faint cottony smudge in the constellations Dorado and Mensa. For centuries it has been part of the background scenery, a hazy patch you might notice on a dark night and then forget. We knew it held star clusters, gas clouds, and supernova remnants. We did not know it was also hosting a silent heavyweight at its core. The first clues did not come from a telescope taking pretty pictures. They came from a mission that does almost the opposite. The European Space Agency's Gaia spacecraft has been quietly measuring the positions and motions of well over 1 billion stars since 2013. Its job is not to zoom in. Its job is to track how stars drift across the sky with exquisite precision, year after year, turning the flat map of the heavens into a moving three-dimensional atlas. When you have that kind of data, tiny oddities in motion start to stand out. Most stars in a galaxy move in smooth, predictable paths, guided by the overall gravity of the system. Their speeds are respectable but not wild, tens or a few hundreds of kilometers per second, following the general rotation of their host galaxy. Every once in a while, though, Gaia catches something stranger. A star sprinting so fast that it looks like it has been flung away by some violent encounter. These are hypervelocity stars moving at hundreds or even thousands of kilometers per second, fast enough in some cases to escape their galaxy entirely. The physics behind them is brutal and simple. Imagine a line of ice skaters holding hands. The skater nearest the center of the line moves gently. The skater on the far end, when the line whips around, is hurled into a much faster arc. In space, a pair of stars or a small cluster can play the role of that line. If they swing past something incredibly massive and compact, that central gravity can tear the group apart, snatching one component inward and whipping the others outward at extreme speeds. The result is a handful of stars racing away as if launched from a cosmic slingshot. In early 2025, researchers sifting through Gaia data noticed several stars in the Large Magellanic Cloud that were behaving exactly like that. They were not just fast, they were fast in a way that pointed back to the same small region of space. Their paths, traced backward through time, converged on a single invisible point, like cracks in glass all leading back to where the stone hit. If these were slingshot victims, something enormous had to be sitting at that meeting point, quietly bending and breaking orbits. That realization triggered the standard modern dance. Other telescopes swung into place. Ground-based observatories measured the stars' velocities more precisely using spectroscopy, turning their light into a measure of how quickly they were moving toward or away from us. Infrared and X-ray instruments looked for any trace of an active source at the center of the inferred slingshot region. If a black hole there were feeding, even modestly, the gas spiraling in should glow. Instead, the images came back stubbornly boring. No bright point, no obvious disk, just stars and faint background fuzz. Yet the gravity was undeniable. By modelling the stars' orbits and speeds, astronomers could estimate how much mass had to be packed into that quiet, central zone to kick them so hard. The number they arrived at was astonishing. Roughly 600,000 times the mass of our Sun, confined to a volume smaller than our solar system. That combination of huge mass and small size has only one known explanation in physics. A massive black hole, dormant now, but fully capable of mayhem when it has access to gas and stars. What makes this discovery so striking is not only the mass of the object, but its silence. Many of the black holes we know best are loud eaters. They tear gas from nearby stars, form hot glowing disks, and launch jets that shout across millions of light years in high-energy light. Those are the easy ones. This one is the opposite. It is not currently accreting enough matter to glow in any wavelength we can see. It is essentially invisible, except for the way it rearranges the lives of the stars that wander too close. Finding a black hole this way by gravity alone is like detecting a hidden whirlpool in the ocean purely from the pattern of shipwrecks around it. You never see the water directly doing anything strange. You just notice that vessels that pass through a certain patch of sea tend not to come out again, and sometimes broken planks shoot away at high speed. It is a more indirect, more delicate kind of detection, and it demands incredibly good data on motions over long times. There is another layer here that changes how we think about our neighbourhood. The Large Magellanic Cloud is not some distant, unrelated system. It is a satellite galaxy that orbits the Milky Way and is gradually being drawn in. Over billions of years, tidal forces will strip its stars and gas, mixing them into our own halo. The newly revealed black hole and its surrounding cluster are likely to end up as part of that merger story. The monster next door is not just a neighbour. One day, far beyond any human timescale, it will be part of our extended family. Scientifically, this dormant black hole solves one problem and creates several new ones. On the one hand, it fits the idea that even small galaxies can host central massive black holes, not just giants like the Milky Way. On the other hand, it suggests that our current census of such objects is wildly incomplete. If a 600,000 solar mass black hole can hide in a galaxy we have been staring at for generations, simply because it is not feeding, how many smaller, quieter ones are scattered through dwarf galaxies and dense star clusters? That question loops back to the theme of this entire year. We used to think the universe would announce its most important structures loudly. Instead, we are learning that some of the deepest truths are whispered in patterns and motions, not in bright lights. Gaia's slow, patient mapping turned a vague smear in the southern sky into a crime scene with fleeing witnesses and an invisible culprit. Other observatories stepped in as forensic experts, tracing trajectories and weighing the unseen. For you and me, there is a different emotional punch. Somewhere in that little patch of southern sky, almost casual to the human eye, sits a gravity well hundreds of thousands of times more massive than our Sun, doing absolutely nothing that we can see. It just waits, warping space, occasionally tossing a star into a wild escape. It is not a threat to us. It is too far and too self-contained. But knowing it is there changes how the night feels. The universe is not only full of light, it is also full of hidden weight. And once you accept that, the next question arrives on its own. If we can find a silent black hole in a nearby dwarf galaxy by watching how it tosses stars around, what else can we find by listening to motions rather than brightness? Because this discovery is not the end of a story, it is the start of a new way of hunting monsters. Once you know there is a 600,000 solar mass black hole hiding in the Large Magellanic Cloud, doing almost nothing, you cannot help wondering what else is out there, sitting quietly in the dark. We grew up with a picture of black holes as cosmic sirens, bright disks, roaring jets, exploding stars collapsing into nothing. In that version of the universe, if something extreme is happening, it will announce itself with a lot of light. The discovery in the LMC cracks that story. It whispers a different message. The biggest influences in the cosmos are not always the brightest. Sometimes they are the ones rearranging everything around them while staying invisible. To find those quiet monsters, you have to stop thinking like a photographer and start thinking like a detective. A camera shows you what glows. A detective watches who moves. That is where missions like Gaia and the new generation of sky surveys on the ground become so important. Instead of taking one picture and moving on, they watch the same stars again and again. They stack data over years. They build movies where the frame rate is slow but the patience is endless. In those movies, odd behavior pops out. A star that wiggles back and forth instead of gliding smoothly tells you there might be an unseen companion tugging on it. A cluster where the stars in one corner move faster than models expect suggests extra gravity hiding in that patch of space. Streams of stars that used to be bound to small galaxies but are now being torn apart by the Milky Way can carry signatures of heavy objects they passed on the way. We already use some of these tricks in our own galaxy. Many of the black holes we know in the Milky Way come from X-ray binaries, where a black hole feeds from a companion star. But there is a growing group that we only see because of motion. A lone star orbiting an invisible partner on a tight, fast path. A binary where one member is dark but heavy enough that the visible star moves in a way that makes no sense otherwise. In each case, gravity does the talking. The Large Magellanic Cloud discovery pushes that idea to a new scale. Here we are not talking about one star and one unseen partner. We are talking about entire groups of stars that have been flung away, their paths converging on a single point where nothing shines. That is a new kind of map. Instead of circling motion around a center, we have radial motion away from a hidden source, like sparks flying out from a grinding wheel. Once astronomers realized they could read these signatures in the LMC, they started to wonder where else the pattern might show up. Dwarf galaxies orbiting the Milky Way are prime suspects. They are small, dense, and old. If they host intermediate mass black holes, a few 100,000 times the mass of the Sun, those black holes might rarely get a chance to feed brightly. Yet over billions of years they would still disrupt orbits, toss stars out, and leave kinematic scars that careful surveys could detect. Globular clusters are another place where gravity might be hiding monsters. These are dense swarms of stars roughly spherical in shape, often containing hundreds of thousands of suns packed into a region only a few tens of light years across. For years, scientists have debated whether some globulars hide central black holes, weighing a few thousand to a few tens of thousands of solar masses. Traditional searches looked for excess light at the core. Now, motion-based methods offer a new way. If the average speed of stars near the center is higher than in the outer regions, and the pattern matches models with a heavy object in the middle, that becomes evidence that something dark is sitting there. We are still early in that hunt. The data are noisy. Stars and clusters bump into each other gravitationally all the time. But the principle is the same as in the LMC. Light tells you part of the story, motion fills in the rest. As our instruments get better, the border between those two ways of seeing will blur. Telescopes like the Vera Rubin Observatory will scan the sky repeatedly, catching subtle changes in position and brightness for millions of sources. Space missions may follow Gaia with even sharper astrometric vision. At the same time, another way of hunting unseen masses has quietly joined the game. Gravitational wave observatories like LIGO and Virgo listen for ripples in space-time from colliding black holes and neutron stars. When two compact objects spiral together and merge, they release energy in gravity waves that wash across the universe. We cannot see those mergers with our eyes, but we can hear them in the stretching and squeezing of space itself. Every detection adds to a census of black holes that would otherwise be almost impossible to catalogue. Those merger signals are biased towards certain masses and distances. They do not reveal every black hole, just the ones that collide as pairs in the right ranges. But they prove a crucial point. Whole populations of compact objects can exist without ever lighting up, and we can still find them through their influence. In one case, it is stars and gas pulled into strange motions. In another, it is the fabric of space ringing like a bell. Either way, brightness is optional. All of this forces us to rethink how incomplete our picture of cosmic structure might be. If dormant black holes are common in dwarf galaxies, if intermediate mass black holes lurk in some globular clusters, if small ones drift in the halos of galaxies with only occasional interactions, then the galaxies we draw on posters are missing a lot of invisible mass in their central regions. That missing weight matters. It affects how stars form, how gas is stirred, how galaxies merge. There is a deeper humility hiding in this shift. For a long time, when we thought about things that were hard to see, we used dark matter as the main symbol, a mysterious substance that interacts through gravity but does not emit light. Black holes were treated as a separate, more dramatic class, rare endpoints of massive stars or seeds of galaxy formation. The more quiet black holes we find, the more they start to feel like part of the everyday scaffolding of the universe, not rare exceptions. They will never replace dark matter in our models. There is not enough mass in them for that. But they remind us that even within the realm of normal matter, there is a vast catalogue of objects we only know by their pull. For you as a viewer, the practical takeaway is strange and beautiful. When you go outside on a clear night and see the Milky Way or the faint haze of the Magellanic Clouds, you're not just looking at a field of lights, you're looking at the visible part of a much larger structure held together and shaped by things that do not glow. Between the bright points are deep wells where space is stretched, stars are deflected, and time itself runs differently, all without a single photon to announce it. The story of the LMC black hole and its speeding victims is one chapter in a larger transition. Astronomy is evolving from a science that mostly counts photons to a science that merges light, motion, and gravity waves into one picture. The monsters we once believed we would always see as blazing beacons are turning out to be subtle, quiet sculptors. They leave trails instead of signatures. They rearrange orbits instead of lighting up the sky. And yet, we are catching them, with surveys that watch patiently, with instruments that notice tiny wobbles, with detectors that feel the slightest tremor in space-time. Each invisible giant we find this way asks the same question. If we missed this for so long, what else are we still blind to? The answer does not make the universe feel smaller or scarier. It makes it feel deeper. There are layers of reality stacked under the layer our eyes evolved to see. The silent black hole next door was our first clear hint. The search for its hidden cousins is only beginning. By the time the story of the silent black hole settled in, another discovery from 2025 had already started tugging at a different part of the imagination. This one was not about hidden mass or invisible monsters. It was about a place, a specific world orbiting a specific star, close enough that you can almost point to its neighbourhood on a star map. GJ 251c, a temperate planet just over 18 light-years away. Not a perfect twin of Earth, not a promised second home, but something maybe more interesting than either of those labels. A real nearby world where liquid water might be possible. 18 light-years sounds absurdly far in human terms. If you tried to drive there at highway speeds, you would be on the road longer than the age of our species. But on the scale of the galaxy, it is the next district over. Our Milky Way is 100,000 light-years across. That makes GJ 251c a neighbour, in the same way another house across the street is a neighbour compared to a city on the far side of the planet. For exoplanet science, that kind of closeness changes everything. The star it orbits, GJ 251, is a red dwarf, much smaller and cooler than our Sun. Stars like this are the marathon runners of the galaxy. They burn through their fuel slowly and steadily, not in a 10 billion year sprint like a Sun-like star, but over 10 trillion years or more. That means any planets in their habitable zones could have a stable source of energy for a span of time that makes all of Earth's geological history feel like a short experiment. Because red dwarfs are dimmer, their habitable zones huddle close. The habitable zone is the range of distances where a planet with the right atmosphere could keep liquid water on its surface. Too close and water boils away, too far and it freezes solid. Around a star like GJ 251, that zone is much nearer in than Earth's orbit is to our Sun. GJ 251c sits inside that narrow band, which is why it jumped near the top of the list of potentially habitable worlds the moment its properties were updated and clarified in 2025. The planet orbits its star once every 54 days. That means a year there is less than 2 months long by our calendar. Your birthday would come around again quickly. That short orbital period also hints at something deeper. Planets that close to their stars around red dwarfs are often tidally locked. The same side always faces the star, just as the same side of our moon always faces Earth. One hemisphere in permanent day, the other in endless night. That setup creates a strange kind of climate problem. The day side could be hot, constantly bathed in starlight. The night side could be brutally cold, locked in darkness. Whether the planet is livable anywhere depends on how well its atmosphere, if it has one, can move heat around. Some models of tidally locked worlds predict a ring of relative comfort around the terminator, the line between day and night. A permanent twilight belt where temperatures are neither boiling nor frozen, where winds carry warmth from the lit side and cold from the dark side, and mix them into something more moderate. GJ 251c is classified as a super-Earth, a term that sounds more dramatic than it really is. It does not mean a perfect Earth copy that has been scaled up like a movie prop. It simply means a planet with a mass a few times that of Earth, likely rocky rather than gaseous. On a surface like that, you would probably feel significantly heavier. Estimates suggest you might weigh between 100 and 120% of your Earth weight, depending on the exact mass and radius. Enough to notice. Like carrying a backpack you cannot take off, not enough to pin you flat. We know about this world at all because of a beautifully indirect technique called the radial velocity method. Planets do not orbit their stars like tiny marbles circling a fixed point. Star and planet orbit together around their common center of mass. When a planet tugs on a star, the star wobbles a little. From our vantage point, that wobble means the star sometimes moves very slightly toward us, and sometimes away. As it does, the color of its light shifts. Light from a star drifting toward us is nudged toward the blue end of the spectrum. Light from a star moving away is nudged toward red. Measure those shifts carefully enough, and you can infer the presence of the planet that is causing them. For GJ 251c, that is exactly what astronomers did. They monitored the star's spectrum over and over, letting tiny shifts in its lines trace out a regular pattern, a 54-day rhythm. That pattern revealed a planet with enough mass to tug noticeably, yet not so massive that it had to be a gas giant. Follow-up observations from different telescopes confirmed the signal. Space-based instruments refined our knowledge of the star itself, which is crucial because the properties of the planet are inferred from the star's behavior. All of that gives us the basics: mass, orbital period, approximate distance from the star, overall level of starlight it receives. But the real reason GJ 251c matters sits just beyond those basics. At 18 or so light years, this planet is close enough that future telescopes might be able to probe its atmosphere directly if the geometry cooperates. That is when a potentially habitable world turns from a line in a catalogue into a real place we can test. The clearest way to study an exoplanet atmosphere today is through transits. When a planet passes directly in front of its star from our point of view, a tiny fraction of starlight filters through the planet's air before reaching us. Different gases absorb different wavelengths. By comparing the star's spectrum during a transit to its normal spectrum, we can detect those fingerprints and say something about what the planet is breathing out into space. This is straightforward for big, puffy worlds. Hot Jupiters and warm Neptunes have thick, extended atmospheres and block a lot of light. Rocky planets are more stubborn. They are smaller. Their atmospheres are thinner. The signatures we want are weaker. On top of that, not every planet transits. The orbit of GJ 251c could be tilted so that, from Earth, the planet always passes above or below the star rather than across its face. If that is the case, the transit trick will not work. Yet even then, all is not lost. Future space telescopes will try more direct approaches, using advanced optics to block out the glare of the star and capture the faint glow of the planet itself in reflected starlight or in infrared heat. The closer the system is, the easier that becomes, because the star and planet appear more separated on the sky. That is why distance matters so much. An exoplanet 50 light-years away is far more challenging than one at 18, no matter how similar they might be in every other way. If and when we do manage to read the air of GJ251c, the game becomes one of biosignatures. On Earth, oxygen in our atmosphere is a classic example. It is so reactive that, left alone, it would disappear as it bonds with rocks and surfaces. The reason it stays high is that life keeps pumping it out. Methane can also play a role, especially when seen in combination with oxygen or other gases that should not coexist for long without constant replenishment. Individual molecules are not enough on their own. It is the patterns and proportions that matter. We have to be cautious here. There are ways to produce oxygen without life, through strong ultraviolet light splitting water and allowing hydrogen to escape. There are ways to make methane through geology. The point is not that any gas equals life. The point is that certain combinations at certain levels, over certain timescales, are very hard to explain with chemistry and physics alone. Red dwarf worlds are especially tricky because their stars can be active, flaring and bathing planets in radiation that changes their atmospheres. That brings us to the double-edged nature of systems like GJ251. On one hand, red dwarfs are everywhere. They are the most common type of star in the Milky Way. If you want to find life elsewhere, odds are high that many of the habitable planets will orbit stars like this. On the other hand, red dwarfs can be hostile. Flares, bursts of charged particles, and long phases of intense youth can strip atmospheres or sterilize surfaces. For a planet like GJ251c to remain friendly, it might need a strong magnetic field, a thick protective atmosphere, or life that hides underground or under oceans. Other famous candidates live in this same category. Proxima Centauri b orbits the nearest star to the Sun, a red dwarf just over 4 light-years away. The TRAPPIST-1 system packs several Earth-sized planets into a tight resonant chain, some in the habitable zone. GJ251c joins that shortlist, not because it is guaranteed to be a living world, but because it is a nearby testable one. Each of these systems is a natural laboratory for learning how often nature manages to thread the needle between enough energy and too much radiation. When you pull back from all the technical details, there is a simple change in feeling that these discoveries bring. For most of human history, other worlds were points of light and poetic guesses. Now, when we say there is a rocky planet in a temperate orbit around a small star 18 light-years away, we mean it in a way that can be checked. We can imagine instruments measuring its spectrum. We can imagine plotting its climate models. We can imagine in some future century sending robotic probes or even human explorers toward a destination with a specific name and specific properties, not just a spot in the dark. GJ251c does not answer the question that Chayava Fools raises about life starting twice in one solar system. It asks a complementary question instead. If life can arise easily, how far from us does it get before we meet it again? The only way to find out is to keep building better eyes, keep picking out the nearest, quietest stars with interesting planets, and keep turning mysterious catalogue numbers into places we can actually study. It is one thing to say a world is in the habitable zone. It is another thing entirely to imagine standing on its surface and asking a simple question. Could anything actually live here? The term habitable is powerful and dangerous. It tempts us into picturing blue oceans and green continents the moment a planet sits at the right distance from its star. GJ251c forces us to slow down. The distance is right. The size might be right. Everything else depends on how this world handles light, heat, air, and time. Start with the star. GJ251 is a red dwarf, cooler and dimmer than the Sun, but not quiet in the way our instincts would like. Many red dwarfs flare, especially when they're young. They release bursts of energetic particles and ultraviolet light that can batter nearby planets. GJ251 appears to be calmer than the most violent of its cousins, which is part of why its planet rose to prominence in 2025. Even so, living next to a red dwarf is more like living next to a slowly crackling campfire than a steady light bulb. Now picture GJ251c itself, a rocky super-Earth, heavier than our world but not by an absurd factor. running around its star in just over 50 days. That close orbit brings with it the likelihood of tidal locking. If so, one hemisphere faces the star forever in unending day, while the opposite hemisphere never sees the star at all. The idea feels like science fiction, but it is simply a consequence of gravity working over long timescales, twisting rotation into alignment with orbit. If you stood at the substellar point, the place directly under the star in the eternal day side, the star would hang motionless in the sky. No rising, no setting, only slow changes in brightness if clouds and haze shifted. Move far enough toward the night side and the star would sink toward the horizon, eventually vanishing behind a permanent wall of twilight. Past that line, you would step into a darkness that never breaks, lit only by stars and perhaps a faint red glow from the thin smear of scattered starlight over the distant dayside. Without an atmosphere, this setup would be brutal. The dayside would bake under constant radiation, driving temperatures far above the boiling point of water. The night side would drop to extreme cold, so low that even gases like nitrogen might freeze out as frost. Rock itself would crack under the thermal stress between these regions. Life, at least anything vaguely like what we know, would have nowhere safe to stand for long. That is why the atmosphere is the deciding factor. With the right kind of air, heat can move. Winds can transport energy from the day side to the night side. Convection can carry warm air upward and outward, while cooler air flows back beneath it in slow global cycles. Climate models of tidally locked planets show that with enough atmospheric mass and the right composition, the contrast between day and night can soften. The permanent day side becomes hot but not apocalyptic. The permanent night side becomes frigid but not infinitely cold. Between them, a belt of twilight can settle into a surprisingly stable environment. For GJ2581c, that twilight ring is where many imaginations go first. Stand there, and the star would hover low in the sky, casting long shadows but never fully setting. The landscape could be a strange mixture of climates. On the side closer to the star, the ground might be dry, perhaps desert-like, baked by intense light slanting in from the horizon. On the side leaning into darkness, frost and ice could dominate. Right on the border, where the balance is just right, liquid water might accumulate in lakes, seas, or oceans. If life exists there, it would be shaped by gradients. Light intensity would change dramatically over distances you could walk. Winds might be strong as air constantly tries to equalize temperature differences. Storms could be common along the Terminator, powered by this relentless tug of war between hot and cold regions. Plants, if there are any, might hug the band where light is steady but not overwhelming. Their pigments might be tuned to the redder glow of the host star rather than the yellow light we're used to on Earth. Even the day and night cycle that life uses as a rhythm here would be different. On a tidally locked world, there is no global day-night switching. Instead, the fundamental cycle could be weather patterns, long-term climate oscillations, or the slow precession of the orbit over many years. Life might mark time by shifts in wind and cloud cover rather than sunrise and sunset. That idea sounds abstract until you remember that even on Earth, many deep ocean creatures live in perpetual darkness and follow tides or chemical flows rather than daylight. All of this remains speculation for GJ251c, because there is a sharp line between what we can infer now and what we cannot. We know the approximate mass and orbit of the planet. We know how much starlight it receives. We do not yet know whether it has an atmosphere, let alone what that atmosphere is made of. We do not know whether it has oceans or continents, magnetic fields or plate tectonics. Those details decide whether a planet in a habitable zone is truly habitable or just technically in the right place. Atmospheric escape is a major concern. Red dwarfs shine more strongly in high-energy light compared to stars like the Sun, especially when they are young. That radiation can strip atmospheres from planets that sit too close. Over hundreds of millions of years, a once thick blanket of air can be eroded away, leaving a bare rock that still sits in the habitable zone but has no water or protection left. To beat that fate, a planet like GJ251c might need a strong magnetic field, volcanic activity that replenishes gases, or a large initial reservoir of volatiles. When future telescopes finally manage to study its air, even a null result will be telling. If we find a clear signature that there is little or no atmosphere, it will reinforce the idea that many red dwarf planets are dry and harsh despite sitting at the right distance. If we do find substantial air, the next question will be its composition. A thick blanket of carbon dioxide could create a super greenhouse, overheating the surface. A mix of nitrogen and carbon dioxide with traces of water vapor, more like Earth, would be more promising. Only after that foundation is clear does the search for life signatures make sense. Looking for oxygen, methane, or other gases related to biology, without knowing whether the planet can even hold an atmosphere, would be like analysing the menu of a restaurant before checking whether the building still exists. GJ2511c is valuable because it is close enough that these steps are not science fiction. They are concrete goals for the next few generations of instruments. There is another way this planet changes the mood of the life question. For a long time, when we asked whether we might be alone, the answers were mostly philosophical. People argued from probability, from the vast number of stars, from the apparent silence of the skies. It was easy to get lost in big numbers and thought experiments. Each nearby potentially habitable world turned some of that fog into a set of measurable tasks. Measure the star more precisely. Measure the planet's orbit. Try to catch a transit. Try to read the atmosphere. Try to track changes over time. You can make a mental list now. Proxima Centauri b, the TRAPPIST-1 worlds, GJ2511c, a few others. For each there is a plan, even if it is still rough. Build bigger telescopes, launch new observatories, develop instruments that can block starlight more effectively. Test techniques on easier targets, and then push down toward the most Earth-like ones. The question "are we alone?" stops being a single overwhelming cliff and becomes a staircase of specific, manageable steps. GJ25p1c sits on one of the lower steps. Close. Accessible in principle. Challenging in practice, but not hopeless. When you think about what life would feel like there, you're not only indulging in imagination, you're rehearsing for the moment when a spectrum appears on a researcher's screen showing the fingerprint of that planet's air. Does it look dead and bare? Does it look warm and cloudy? Does it show a hint of imbalance that might mean biology? Whatever the answer, it will narrow the possibilities. And that is the quiet power of a small rocky world orbiting a dim red star 18 light-years away. It makes the search for life feel less like a dream and more like an investigation. Not a story we tell ourselves to feel less alone, but a series of tests that either the universe will pass or it will not. If we learn that GJ2511c is empty, we will update our sense of how hard life is. If we learn that it is rich in interesting chemistry, we will update our hope. Either way, the question moves from mood to measurement. By the time you have wrapped your head around nearby temperate planets and quiet black holes in neighboring galaxies, the universe pulls its favorite trick. It asks you to imagine a time when none of that existed yet. No Milky Way, no Sun, no Earth. Just the young cosmos, still glowing from its own birth. Then it drops a bombshell. In 2025, the James Webb Space Telescope stares into that early era and finds something that should not be there. A fully grown, supermassive black hole, already feeding, already reshaping its home galaxy, only about 570 million years after the Big Bang. On the human timescale, 500 million years sounds like forever. On the cosmic timescale, it is infancy. If you compressed the entire history of the universe into a single year, this black hole would appear in the first few days of January. Galaxies are just beginning to assemble. Gas is still falling together along filaments. Stars are flickering on in dense little knots. In our standard story, this should be a messy construction site. The cosmic version of a field with scattered saplings and broken rocks, not towering trees. The galaxy hosting this anomaly carries the label Canucks LRD8.6. The name comes from the survey that first spotted it, and the redshift that tells you how far back in time you're looking. Redshift is a measure of how much the expansion of the universe has stretched the light. At values near 9, you are appearing less than 600 million years after the beginning. That alone is impressive. Webb was built to reach that deep. What no one expected with high confidence was to find, in such a young galaxy, firm evidence of a central engine that massive. To understand why, step back and ask what a supermassive black hole actually is. The ones we know best sit in the centers of galaxies. The black hole in our own Milky Way, Sagittarius A, weighs about 4 million times as much as the Sun. Some in larger galaxies reach billions of solar masses. These monsters are not born that way. They grow. The standard picture says you start with small seeds, black holes formed when very massive stars collapse at the ends of their lives. Those seeds then gain weight slowly by pulling in gas, dust, and sometimes entire stars. Growth is not unlimited. When material falls toward a black hole, it forms a disk that heats up and shines. That light pushes back on the material that is still falling. If the infalling gas tries to come in too fast, the radiation pressure pushes it away. There is a natural upper limit to how quickly a black hole can eat, set by the balance between gravity pulling in and light pushing out. Astronomers give that limit a formal name, but the idea is simple. Even the hungriest black hole has a maximum sustainable feeding rate. When you run the numbers, you hit the problem. Start with a black hole maybe 10 or 100 times the mass of the Sun. Let it grow as fast as physics reasonably allows. It still takes hundreds of millions of years to reach millions or billions of solar masses. That timeline is tight already. It gets even tighter when you realize that the early universe was not a calm buffet. Gas was turbulent. Star formation was violent. Black holes could be starved by feedback or blown clear of their best feeding grounds. Now place that slow growth model next to the Webb data from Canucks LRDZ 8.6. The galaxy shows a bright, compact source at its center, glowing in a way that almost screams accretion disk. Spectra reveal broad emission lines, light from gas orbiting close to a massive object at high speed. By fitting those lines with models of how gas moves near a black hole, astronomers can estimate the mass of the beast doing the pulling. The answer lands in the uncomfortable range. Hundreds of millions of solar masses, not a baby, something well into adulthood, cosmically speaking. You can picture the tension like this. Walk into a field that was scorched by fire less than a year ago. You expect ash, sprouts, maybe some seedlings. Instead, you find a fully grown oak tree with a thick trunk and wide branches casting shade. You do not just say how nice, you ask how in the world that happened. Did the tree start from a giant seed? Was there an older root system left over that you missed? Or is your entire understanding of how trees grow missing something important? The same questions are now aimed at the early universe. One family of ideas says that our assumed seeds were too small. Instead of starting from dead stars, maybe some regions of the young cosmos collapsed almost directly from gas clouds into black holes of 10,000 or 100,000 solar masses. That would jumpstart the process. With bigger seeds, you need fewer exponential growth cycles to reach the huge masses we observe. The catch is that you need to explain what special conditions allowed gas to collapse so cleanly without fragmenting into normal stars. Another set of ideas points to star clusters. Imagine a dense swarm of massive stars in a small region. They orbit, interact, and sometimes collide. Over time, these runaway collisions could build an extremely massive star that then collapses into a big black hole. That new hole could sit at the center of the cluster and grow further. It is a neat story, but the math is harsh. You need extreme densities and you need to do it fast before the cluster flies apart or feedback from radiation blows out the gas. There are even more adventurous proposals, from exotic dark matter effects to subtle changes in early cosmic chemistry. None of them have the same clean elegance as the standard model where black holes grow slowly inside galaxies over billions of years. That is exactly the point. Webb is showing us a reality that the clean story does not quite match. The universe has clearly found at least one route to building enormous black holes very early. Our job is to work backward from that fact and figure out the path. Webb's power in this game is not just its sensitivity, but its ability to separate light from different sources. In Canucks LRDZ 8.6, you can distinguish the glow of young stars from the hotter, more compact emission of the active nucleus. That tells you the galaxy is doing two extreme things at once. It is forming stars at a high rate and feeding a central black hole that is already massive. In older galaxies nearby, we sometimes see a tight relationship between the mass of the central black hole and the mass of the surrounding stellar bulge. In this young system, we may be catching that relationship in the act of forming. That raises another unsettling question. Which came first, the big galaxies or the big black holes? For years, the safe answer was that they grew together in lockstep. Gas flows into a galaxy, makes stars. Some of those stars end their lives as black holes. Those merge and accrete, and everything scales together. Now, when we see an active black hole this heavy in such a young galaxy, we have to consider the possibility that black holes sometimes jump ahead, shaping their hosts in a top-down way instead of growing as a side effect. This is where the mood of the field shifts from quiet satisfaction to excited discomfort. On the one hand, it is thrilling. The universe is giving us puzzles again, not just confirming our expectations. On the other hand, it means that cherished models may need to be bent or even broken. That is not failure. That is the core rule of the game. Observations are the judge. Theory is the story we tell to fit them. When the fit gets bad enough, you change the story. The 2025 detection of this supermassive black hole is not alone. Webb has been turning up other early galaxies that look too massive, too organized, or too chemically mature for their age. Some of those will turn out to be quirks of measurement. Some will stand. Together they paint a picture of a universe that may have built structure faster and more efficiently than our first generation of simulations assumed. Maybe gas collapsed more easily in certain regions. Maybe early stars were more massive on average. Maybe mergers happened in brief, furious bursts. From the outside, it might sound like we are losing control of the narrative. In reality, this is the healthy part of science. You build a model, you test it, you find where it fails, you refine it or replace it. In the 1990s, the idea that the expansion of the universe was accelerating sounded wild. Then, evidence for dark energy piled up and cosmology shifted. Now, in a similar way, Webb is pressuring our ideas about how quickly complexity can arise. When you look at the deep field image containing Canucks LRDZ 8.6, you do not see anything that looks obviously wrong. Just faint smudges, each a galaxy trillions of kilometers across, frozen from a time when the universe was young. Hidden in one of those smudges is a black hole that grew faster than our textbooks predicted. It does not roar, it simply exists, quietly forcing us to admit that the early universe had more tricks up its sleeve than we thought. And that is the thread connecting it back to everything else in this strange year. A big interstellar comet telling us that planetary systems share their debris. A new moon of Uranus reminding us that our own system is still incomplete. A suspicious rock on Mars pushing us to define what proof really means. A nearby exoplanet asking whether habitable is more than a word. Now, an ancient black hole that should not exist yet, standing like a fully grown tree in a field that was supposed to be bare. If the observation holds, theory must bend. That has always been the deal. The sky is not here to flatter our expectations. It is here to tell us how things actually work, as long as we are willing to listen and to rewrite our stories when the universe refuses to follow the old script. After the shock of a supermassive black hole turning up far too early in the universe, you might hope that everything else in the young cosmos would at least behave. Galaxies that look like cosmic train wrecks, stars forming in frantic bursts, chaotic shapes that barely deserve the name galaxy yet. That was the comfortable picture. Then Webb pointed its mirrors at another deep field and ruined that comfort in a very specific way. There, in a slice of space from about 1.5 billion years after the Big Bang, sat a galaxy with a name that sounds almost poetic, Alaknandanda, calmly showing off spiral arms it should not have had time to grow. To understand why this is strange, it helps to think about what a spiral galaxy actually is. The Milky Way is one example, with a bright central bulge and long arms winding out like the pattern on a whirlpool. Those arms are not solid structures. They are waves of higher density that move through a rotating disk of stars and gas. As gas enters a spiral arm, it is compressed, forms new stars, then drifts out again. Maintaining that pattern for billions of years requires a delicate balance between gravity, rotation, gas inflow, and the disruptive explosions of dying stars. That kind of balance is usually associated with age. In the nearby universe, spiral galaxies are often the elders of the cosmic neighborhood. They have had time to settle, to digest violent mergers, to cool gas into a thin disk where ordered rotation dominates over random motion. When you look farther back in time toward the early universe, you expect the opposite. The average galaxy there should be messy, thick, and clumpy. More like a half-built city under construction than a finished downtown with clean streets and predictable traffic. Alaknandanda does not fit that expectation. In Webb images, it does not appear as a fuzzy blob or a jagged knot. You can trace a disk, see hints of a central light concentration, and even pick out the beginnings of spiral structure. For a galaxy living only about 1.5 billion years after the Big Bang, that is like meeting a teenager who already runs a well-organized company. It is not impossible in principle. It is just statistically weird enough that you start to question your story about how long maturity should take. The weirdness is not only in the shape. By splitting the light from the galaxy into a spectrum, astronomers can estimate its rate of star formation and its chemical makeup. New stars form from gas clouds that are mostly hydrogen and helium. As generations of stars live and die, they forge heavier elements and spread them back into the galaxy through winds and supernova blasts. More heavy elements usually means more generations. In Alacnandanda, the chemical mix looks surprisingly enriched for such an early time. Not wildly overdone, but suggestive of a galaxy that has already cycled gas through stars several times. At the same time, its current pace of star formation is not a wild starburst. It is not burning through its remaining gas in a desperate flare of activity. Instead, it seems to be forming stars at a steady, controlled rate. Enough to keep the galaxy growing, not so much that it blows itself apart. It is this combination that led one researcher to describe it as a galaxy with too much self-control, young in the cosmic calendar, but already behaving like a system that has learned to regulate itself. Here is why that is so troubling for our models. In the standard story, the early universe is a rough neighborhood. Galaxies assemble through frequent mergers. They crash into each other, stir up gas, trigger violent bursts of star formation, and leave behind disturbed shapes that have to relax over long times. Only after many such events do the survivors settle into stable disks and spirals. Finding a settled disk so early suggests either that this galaxy somehow dodged the worst of that chaos, or that our picture of how quickly disks can form is incomplete. One possible escape route is environmental. Maybe Alacnandanda grew in a region of space where its neighbors were relatively small and gentle. Instead of enduring repeated head-on collisions, it might have quietly absorbed gas from the cosmic web and tiny satellite galaxies, building mass without having its disk shredded. Gas could have streamed in along filaments, feeding star formation in a more continuous way, like a steady diet rather than a feast and famine cycle. Another route is internal. Perhaps the physics of gas cooling and settling into a disk in the early universe is more efficient than our simulations assumed. If gas can shed its random motions and fall into ordered rotation more rapidly, then disk galaxies could appear sooner than expected. Feedback from young stars and from whatever black hole sits in the center might help regulate the process, blowing out just enough gas to prevent runaway star formation without destroying the emerging spiral. Both of these possibilities are being explored in computer models now. Simulations that once assumed a slow, bottom-up growth are being rerun with different initial conditions, different recipes for how gas heats and cools, and different treatments of feedback. When you tweak those knobs, spirals can indeed form earlier in some cases, especially in halos that avoid the most violent mergers. The challenge is to produce galaxies that look like Alacnandanda without ruining the good agreement with other observations. There is another puzzle layered on top. In the nearby universe, there is a tight empirical relationship between the mass of a galaxy's central black hole and the mass of its inner stellar component. It is as if galaxy and black hole grow in step, keeping a kind of cosmic balance. In Alacnandanda, we do not yet have a clear measure of the central black hole, but given what Webb has shown in even younger systems, it is natural to wonder whether an overgrown black hole is already there, helping to regulate the galaxy from the inside. If that is true, then the early universe was not only building galaxies faster, it was also establishing the same kind of black hole galaxy partnerships we see today on a compressed schedule. That would mean feedback from active nuclei, even brief episodes of intense feeding, could have helped clean out gas from the central regions, allowing disks and spirals to form without collapsing entirely into thick bulges. For you and me, the technical debate boils down to a simple image. We once pictured the early universe as a toddler phase for galaxies, all sharp edges and mood swings, with elegance coming much later. Webb is forcing us to admit that some regions looked surprisingly grown up very quickly. Giant black holes in baby galaxies, structured spirals in a time when chaos was supposed to rule. The cosmic timeline is not a smooth ramp. It is more like a landscape with pockets where evolution ran ahead of schedule. There is a risk of overcorrecting here. For every Alaknandanda, there are many young galaxies that do look messy, clumpy, and violently assembled. The early universe is still, on average, a rough place. What has changed is that we can no longer pretend that maturity was impossible that early. Instead, we have to explain why some patches of space produced early bloomers, while others lagged behind. That in turn feeds back into the biggest questions in cosmology. How do tiny fluctuations in the density of matter, just after the Big Bang, grow into the web of galaxies we see today? How does dark matter guide gas into halos? How do stars and black holes jointly shape their environments through energy and winds? Every time Webb hands us an outlier like Alaknandanda, it is highlighting a part of that story we have glossed over. There is also a strange symmetry with our more local discoveries from this same year. In the deep past, we find a spiral that settled down too quickly. In our own time, we find that Saturn holds far more small moons than we counted, that an asteroid near Earth has been quietly sharing our orbit for decades, that a main belt rock like Donald Johanson can still surprise us up close. Far away, the universe matured faster than we thought. Close in, we have been slower to notice the details than we would like to admit. Taken together, these lessons nudge us toward the same conclusion. The cosmos does not arrange itself according to our sense of a tidy timeline. Structures can grow up early. Others remain half-finished for billions of years. Our job is not to force everything into a single neat arc, but to map where and how the universe chose to sprint or stroll. Alaknandanda is a signpost in that map, a spiral galaxy with too much self-control, quietly winding its arms in a time when the script said it should still be a chaotic blur. After spending time with galaxies that grew up too fast and black holes that arrived too early, it is tempting to look back at our own solar system and feel a kind of relief. Out there, the universe is wild and surprising. In here, we think, everything important has already been catalogued. The planets are known. The big moons have names. The main asteroid belt is just background texture. In 2025, that comforting picture did not survive contact with reality. The closer we looked, the more our own backyard started to feel like an unfinished draft. Take Lucy. On paper, this mission is all about the Trojan asteroids near Jupiter, those ancient companions that share its orbit and carry the chemistry of the early solar system. But before Lucy heads out to that distant swarm, it had to test its instruments on something closer. The target was a modest main belt asteroid named Donald Johanson, chosen not because it was dramatic, but because it was convenient. From Earth, Donald Johanson was a moving dot in a band of many similar dots, a practice rock. When Lucy flew past, that practice rock transformed. The images that trickled back showed a peanut-shaped body, two lobes joined at a narrow neck like a frozen embrace between worlds. That shape is what astronomers call a contact binary. Once, there were likely two separate objects orbiting each other slowly. Over time, they spiraled together and fused in a low-speed collision. If they had hit harder, they would have shattered instead. The fact that they merged and stayed intact preserves a snapshot of gentle assembly in a violent region. The surface was pitted with craters of different sizes and depths. Small sharp-edged craters sat on top of larger, softer ones. In planetary science, that layering is a timeline. Big impacts tend to happen early, when there is more debris flying around. Smaller hits continue for billions of years. By reading which craters overlap which, you can reconstruct a rough history of bombardment. Donald Johanson turned out to be less a random rock and more a diary page from the early solar system, written in impacts. None of that was obvious from telescopes alone. From Earth, even with big mirrors, the asteroid was just a point with a brightness and a slightly changing colour. The contact binary shape, the crater record, the subtle variations in surface texture, all of that required getting close. Lucy was built for another destination, yet its first real encounter reminded us of a simple truth. Until you actually visit, you do not know how much you do not know. If the asteroid belt still has secrets at that scale, you might expect that near-Earth space, which we watch constantly, would be thoroughly understood. In August 2025, that assumption took a hit. Astronomers tracking small bodies in Earth's neighbourhood flagged a new object with a familiar label pattern. An unassuming designation, 2025 PN7, just another small rock passing through. Then they calculated its path more carefully. The orbit did not match the usual near-Earth profiles. It seemed to be doing something stranger. It was staying near us. The term for what 2025 PN7 turned out to be is quasi-satellite. It sounds like a half-promise, and in a way it is. This object does not orbit Earth directly the way the Moon does. Instead, it orbits the Sun, just as we do, with almost exactly the same period. Because of that matching rhythm, when you look at its motion from Earth's perspective, it appears to loop around us in a complex path. Sometimes it drifts ahead in our orbit, sometimes it lags behind, tracing a lopsided pattern over many years that keeps it nearby without ever being truly captured. On a diagram of orbits, the distinction matters. Earth's true satellite is bound primarily by our gravity. A quasi-satellite lives in a delicate dance between the pull of the Sun and the pull of Earth. On a human level, though, the effect is simple. For decades, a small object has been sharing our orbital lane, hanging around in our neighbourhood, and we did not notice. Only in 2025, with improved surveys and more sensitive tracking, did its path stand out clearly enough to earn a name. The size of 2025 PN7 is modest, probably a few tens of meters to maybe 100 across. Too small to be a world of its own, large enough to survive atmospheric entry and cause real damage if it ever hit. There is no sign that it is on a collision course. Its looping path seems stable for now. The point is not that we discovered a new threat. The point is that we discovered a new relationship. Earth's orbit is not a pristine track with a single companion. It is a lane with small fellow travellers that come and go over long timescales. This is not the first quasi-satellite we have found, but the fact that a new one popped up in 2025 is a reminder that even in the near-Earth zone, our inventory is incomplete. Detection depends on brightness, which depends on size, reflectivity, and distance. A slightly darker rock on a slightly different loop could have remained invisible for much longer. We like to imagine that if something is sharing our orbit, we would know. The reality is that our map is still being drawn. While we were revising our mental picture of the inner solar system, the outer system quietly staged a coup in the record books. In the middle of 2025, observational campaigns and careful reanalysis of past data led to a headline that sounded almost like a joke. Saturn had gained 128 new moons. Its total count jumped to 274. No new physics was involved, no sudden creation event. We had simply looked harder and for longer, and the sky paid us back in numbers. The new moons are tiny by planetary standards. Many are only a few kilometers across, irregular lumps of ice and rock following stretched, tilted paths far from the planet. Some move in the same direction as Saturn's rotation. Others orbit backwards, a sign that they are likely captured objects rather than children of a disk that spun with the planet from birth. They are fragments, leftovers from past collisions, or bodies snagged from passing populations and held by Saturn's gravity. Finding them required deep images taken over long exposures, then stacking those images and tracking faint moving points across them. It is painstaking work. Each detection has to be checked to make sure it is not noise, not a background star, not a transient artifact. And each new moon has to be observed more than once to confirm its orbit. The reward for that patience is a census that reveals how busy the outer reaches of Saturn's influence really are. Here again, the symbolic punch is larger than any individual rock. We used to recite the number of Saturn's moons as if it were a fixed property. First a few, then dozens, now hundreds, with more likely to be added as techniques improve. The threshold for calling something a moon is simple. It must be gravitationally bound to the planet and trace a stable orbit over long spans of time. There is no minimum size written into the universe. The limit is our ability to see. Put Lucy's close-up, Earth's quasi-satellite, and Saturn's moon explosion next to each other, and a pattern emerges. Our solar system is not a finished book. It is an active file, full of annotations we have not yet read. Asteroids still surprise us when visited. Near-Earth objects can share our orbit quietly for years before we notice. Giant planets carry swarms of small companions we have only begun to count. Everywhere we tighten our focus, the complexity goes up. This has practical consequences. Defending Earth from hazardous impacts requires more than tracking a few famous near-Earth asteroids. It requires understanding the full population of small bodies, including odd cases like quasi-satellites and unusual resonant paths. Planning missions to outer worlds means navigating through thick fields of tiny moons and ring particles, where every uncharted piece of debris is a potential risk and a potential target. It also shifts something in the way we feel about the discoveries from earlier parts of this story. When we hear about strange galaxies or ancient black holes, it is easy to file them under distant wonders, relevant to theory but not to daily experience. When Lucy sends back an image of a battered contact binary, or when a new object like 2025 PN7 appears in the catalogue, or when Saturn's moon count jumps by more than 100 in one stroke, the message comes home. The same universe that breaks our expectations on the larger scales is still busy rewriting the details right next door. In that sense, the solar system is not a static museum of relics. It is an active crime scene, full of clues about collisions, captures, and slow gravitational dances that are still ongoing. Every new moon, every odd orbit, every cratered, peanut-shaped rock is evidence. Taken together, they tell a story of a system that never really settled down, only slowed enough for us to start catching up. And as 2025 drew toward its end, one more result arrived that tied all of these threads together in an unexpected way. A measurement not of a rock or a moon or a black hole, but of us. Specifically of how fast our entire solar system is moving through the cosmos. A number we thought we already knew suddenly shifted. The reality check turned outward again, and the universe quietly informed us that even our sense of motion was due for an update. If you step outside on a clear night, it feels like you're standing still under a sky that is also standing still. The ground is solid, the stars are fixed. Nothing in your body tells you that you are moving at all. Intellectually, you might know that Earth spins and orbits the Sun, but it feels like trivia, not like a physical experience. Then 2025 hands you a result that reaches right into that quiet feeling and shakes it. A careful measurement that says our entire solar system may be rushing through the universe far faster than we thought. We already knew we were not sitting still in space. Earth spins once every day, carrying you around at hundreds of meters per second depending on your latitude. Earth orbits the Sun at about 30 kilometers per second. The Sun orbits the center of the Milky Way at roughly 230 kilometers per second. The Milky Way itself moves relative to nearby galaxies. Each of those motions stacks on the others, so there is no meaningful sense in which we are at rest. The natural question is always compared to what? For a long time, the best answer to that compared to what question was the cosmic microwave background. That faint glow that fills all of space, leftover radiation from the hot early universe, acts like a fog that surrounds every galaxy. If you are moving through that fog, it looks slightly hotter in the direction you're heading and slightly cooler behind you. Hotter means the light has been squeezed a little by your motion. Cooler means it has been stretched. In the 1980s, satellites measured that temperature difference across the sky and found a clear dipole pattern. From that dipole, you can infer a speed. The standard value that ended up in textbooks is a bit under 400 kilometers per second for the motion of the Sun relative to that cosmic background, in a direction roughly toward the constellation Leo. Combine that with the Sun's orbit in the Milky Way and other motions, and you get a picture that felt satisfying. We had a cosmic rest frame. We knew how fast we were drifting through it. It was one of those numbers that settled in and became part of the furniture of cosmology. Then radio astronomers tried to measure the same motion in a completely different way. The logic was elegant. If the universe is close to uniform on large enough scales, then very distant galaxies should be spread almost evenly across the sky. Your motion through that distribution should create a slight imbalance. You would see a bit more radiation and a slight excess of sources in the direction you're moving because of subtle effects of Doppler boosting and aberration. On the opposite side of the sky, you would see a slight deficit. With that idea in mind, teams used large radio surveys to count and weigh distant galaxies. Early attempts with older catalogues hinted at something odd. The preferred motion direction lined up roughly with the microwave background result, but the speed implied by the pattern was higher. That could have been a fluke. The data were noisy. The sky coverage was not complete. Systematic errors were lurking everywhere. For years, the safest line was that the tension was interesting but not decisive. In 2025, that changed. New surveys with more sensitive arrays and better calibrated catalogues pushed the method further. Instead of a mishmash of instruments, astronomers had cleaner maps of radio galaxies over huge swathes of the sky. When they performed the same dipole analysis again, the pattern snapped into focus. The direction of motion still matched, but the amplitude of the effect pointed to a speed for our solar system of more than 1,000 kilometers per second, relative to the large-scale structure traced by those distant galaxies. Roughly 3 times the standard microwave background value. If you translate that into everyday language, it sounds surreal. Right now, as you listen, you may be sitting in a chair or lying in bed. On cosmic scales, you may also be hurtling through space at over 1,000 kilometers every single second relative to the deepest structures we can map. It does not make your stomach lurch, it does not rattle the windows, it just quietly makes a mockery of our intuition about stillness. The real tension is not emotional though, it is scientific. 2 different methods, both grounded in physics, are supposed to be measuring the same thing: your motion relative to the universe on very large scales. One uses the cosmic microwave background, the other uses the distribution of faraway radio galaxies. They agree on the direction, they disagree on the speed by a factor that is too big to shrug off as rounding error. If both measurements are right, something in our assumptions about how uniform the universe is, or how we interpret one of these signals, has to give. The first suspects live in the boring drawer. Maybe the radio surveys are still contaminated by local structures. Our patch of the universe is not perfectly smooth. Clusters, voids, and superclusters can create real imbalances in how many galaxies you see in a given direction. If you have not gone far enough out in distance, or if your sample is biased in subtle ways, you might attribute some of that real structure to a fake motion. Perhaps the catalogues still have calibration offsets between hemispheres. Perhaps some populations of radio galaxies evolve with time in a way we have not modelled correctly. On the other side, maybe the microwave background dipole is not purely kinematic after all. The standard picture says the entire temperature difference across the sky at that large scale comes from our motion through an otherwise uniform background. But in principle, very long wavelength fluctuations in the density of matter could imprint a small extra dipole pattern. If that contribution is larger than we thought, then using the microwave dipole as a clean speedometer would be slightly wrong. There is also a more radical possibility. The cosmological principle, the idea that the universe looks roughly the same in all directions and at all locations when viewed at large scales, might not hold quite as neatly as we assumed. Most of modern cosmology is built on that principle. It works extremely well for explaining the overall pattern of galaxies and the detailed fluctuations in the microwave background. Yet if our region of the universe sits in a larger scale flow, or if there are coherent structures on scales bigger than we have mapped, then our motion relative to matter and our motion relative to the background light might differ in subtle ways. No one is eager to tear up the foundation. The first priority, and the work already underway, is to test and retest every step in both measurements. New microwave background missions can refine the dipole to even higher precision. Next-generation radio surveys and optical catalogues will expand the sample of distant galaxies, improve sky coverage, and allow the same dipole analysis to be repeated with different types of sources. If the tension shrinks as the data improve, it will become a footnote in the history of a method growing up. If it persists, the pressure on the models will rise. In the meantime, the image is hard to shake. Every second, our solar system is surfing through space at a speed that would carry you from New York to London in less than a blink, relative to the deep structure of the cosmos. The fact that you feel nothing is not a bug. It is a reminder that frames of reference are everything. You're at rest with respect to your chair. Your chair is at rest with respect to the floor. The floor is at rest with respect to Earth. Each layer hides the motion of the next, until only careful instruments looking outward reveal the full stack. If you line up the discoveries of this year, a pattern emerges. A large comet from another star tells us that planetary systems share material more freely than we assumed. A new moon of Uranus shows that even familiar planets still have hidden companions. A stubborn rock on Mars pushes our standards of proof about life. A quiet black hole in the Large Magellanic Cloud and a too-early monster in a distant galaxy both say that gravity has been working in ways our models did not fully capture. A nearby exoplanet reminds us that words like habitable are only the start of the story. And now a revised estimate of our own speed hints that even our cosmic coordinates may need updating. None of these results breaks the universe. They break our stories about the universe, which is exactly what good observations are supposed to do. We can respond by clinging to the old stories, or we can treat each surprise as a doorway, a chance to ask better questions, build better tools, and accept that our picture of reality is always a draft, never a final document. So as this quiet revolution of a year comes to a close, imagine yourself not as a tiny figure under a static sky, but as part of a moving system, riding a spinning world that orbits a star, that circles a galaxy, that plunges through the cosmic background at a speed your body will never feel. The same physics that hides that motion from your senses also lets us reveal it with careful work. The universe will keep its pace whether we measure it correctly or not. The choice we face is whether we are content with comforting numbers or willing to be unsettled by truer ones. In 2025, the sky answered that question for us in a dozen different ways. It refused to stay inside the lines we'd drawn. It moved faster, formed structure sooner, hid more quietly, and reached closer than we expected. In doing so, it gave us something better than certainty. It gave us room to grow.